Okay, thank you. So thank you very much for the opportunity to speak here and so on. It's nice to be able to see the audience and see so many familiar faces. It's nice that this meeting could actually take place despite all the difficult conditions and so on. So what I'm going to talk about is some joint work with Giovanni Russo, who I can also see is online, so he can also field some questions if necessary. Most of what I'm going to say is in a couple of papers we have listed at the bottom here. So we've been looking at nearly Kähler manifolds, particularly in dimension 6, and trying to exploit some torus symmetry. So you don't get disappointed too far into the talk, we're not producing any new compact examples, but we're trying to get some structural theory and trying to understand some properties when there is a torus symmetry around. So I want to start by giving some general background on nearly Kähler manifolds, which will be familiar to some people, and set up my notation, and then our main tool is going to be the notion of multi-moment map. So I'm going to explain how that works in this situation. And so this is some generalization of symplectic moment maps that's appropriate in a number of other situations when you don't necessarily have closed forms of degree 2. And just like with symplectic situations, you can talk about reduction. So at regular values, so I will be telling you what geometry you get when you reduce a regular level value, and we have some information about what happens at critical values of such multi-moment maps. And it gives some hopeful picture of some of the structure. But so let me start by recording the notions of nearly Kähler geometry, and if there are questions at any time, then please do ask. When I say nearly Kähler, I'm always going to mean strict nearly Kähler. So these are special types for almost Hermitian manifolds. I'm going to call my complex structure J, and that's compatible with the G, metric G. And the nearly Kähler condition is that nabla J is skew symmetric. So nabla xj on the same x is always 0. And then I want these things not to be Kähler, so that's the strict word here. So I'm going to require that J is not parallel. And here nabla here is the Leverage-Vita connection of the metric. So these were introduced a while ago, actually the year I was born. So in the paper of Gray in 1965. And studied by Gray in many papers following that, 10 years after that, following 10 years or so. One of the important results that came more recently is by Paul Andy Nagy, who gave a general structure theory for nearly Kähler geometry. So here I'm dropping the word strict, I guess, for the moment, or maybe I have some factors that are not strictly nearly Kähler, but Nagy's result can be phrased in this way: if we have a complete, simply connected nearly Kähler manifold in any dimension, then it's a product of a Kähler manifold, a three-symmetric space, or several three-symmetric spaces, twistor spaces of positive quaternion Kähler manifolds, and nearly Kähler 6 manifolds. So Kähler manifolds are a well-known class, of course, and they don't satisfy the strict condition. But when I take a product of a Kähler manifold with them, one of the other examples, I get a strict nearly Kähler manifold. Three symmetric spaces are well-known analogues of ordinary symmetric spaces, and there are classification theorems for those. So they're homogeneous spaces with a symmetry of order 3. So there's a known list of those spaces, or known classification theory of those spaces. Then twistor spaces of positive quaternion Kähler manifolds. We would know what those are if we knew what all the positive quaternion Kähler manifolds are. And that's, of course, a big open question of what that list of manifolds is. whether there are any positive complete positive quaternionic Kähler manifolds that are not Wolf spaces, so symmetric spaces. And then there is this last interesting category here, which is the nearly Kähler manifolds in dimension 6. So I pulled up this result early because it highlights that understanding nearly Kähler manifolds in dimension 6 is a central problem for understanding nearly Kähler manifolds in general. And the other central problem is understanding the positive quaternion Kähler manifolds. So this talk is going to be focused on dimension 6. As dimension 6 is very nice in nearly Kähler geometry. So Gray proved that in dimension 6, nearly Kähler manifolds are automatically positive Einstein spaces. So if I'm looking in the complete case, then they will be compact, and pi1 will be finite, so it's not any loss of generality, assume they're simply connected. The homogeneous examples are known, so they fall into this category of 3 symmetric spaces, and there are exactly 4 examples in dimension 6. So there's a 6th sphere thought of as the unit sphere inside the imaginary octonions. So that has a symmetry group, naturally a symmetry group G2, the compact form of G2 with isotropy SU3. There's complex projective 3 space with symmetry group SP2. So it's not the Fabini Studi metric here. But, then there's the flag manifold SU3 over T2. And finally, is a product 2-3 spheres written as regard as a 3 symmetric space. You take 3 copies of SU2 and divide out by a diagonal SU2 subgroup. So the 3 symmetric property is very clear there. It's just given by permuting the 3 factors. So that's a nice concrete list. These were actually constructed by Wolf and Gray in the 60s, but it was first in 2005 that Butroy completed the proof that this actually is the full classification of the homogeneous examples. So these examples have been known for a long time, but they were the only compact examples that were known for many years. There's been some study of these nearly Kähler manifolds in dimension 6 via killing spinors, and there's been nice relations to their Riemannian cones. So one nice characterization in nearly Kähler geometry is that the Riemannian cone is automatically a polynomial G2. So this but all these different angles are looking at nearly Kähler resulted in 2017 by Foscolo and Haskins actually constructing new compact examples. So they live on 2 of the spaces that are already on my list, on S3 cross S3 and on S6. They're no longer homogeneous, but they're constructed as cohomogeneity 1 examples. And the principal orbit here is SU2 cross SU2 divided by a diagonal U1. So the principal orbit is a copy of a 2-sphere product with a 3-sphere. So this was a big piece of news when this result came out in 2017, and it's very good to have extra examples that are not homogeneous spaces. The general approach of the Foscolo-Haskins proof is much like the Christoph Böhm's approach for producing cohomogeneity 1 Einstein metrics on spheres in middle dimensions. So these are implicit solutions that are abstractly shown to exist. And so on. But these add 2 extra solutions to the list of 3 symmetric examples. So let me have a look at the symmetry groups again of these examples. So I put them up in this table. So let's look at the connected automorphism groups of the almost Hermitian structure we have. So preserving G and J. So for the three symmetric groups, it's just the symmetry groups I wrote down in the previous table. So G2, SP2, SU3, and SU2 cubed for 6 sphere and S3 cross S3. And then the cohomogeneity 1 examples from Foskler and Haskins, they have SU2 squared symmetry. So the simple observation here is that all the groups that appear here, they have rank at least 2. So G2 is a simple group of rank 2, SP2 is rank 2, SU3 is also rank 2. SU2 cubed, of course, is rank 3, so this is higher rank, but at least all of these have a symmetry group of rank 2. So it makes sense to try and ask whether what you can say about nearly Kähler manifolds with a two-dimensional abelian symmetry group. And the only space on this list that has higher symmetry rank is the S3 cross S3 example. So they have 3 copies of SU2. So Moriano and Paul-Andy Nagy again, they studied the situation when you have a 3-torus symmetry. In particular, they proved in that work that actually the maximal rank of a torus acting on a nearly Kähler manifold is 3. So, currently the only example we have that is compact with that property is this S3 cross S3 example with its 3 symmetric metric. So it's an open question at the moment whether there are other examples with rank 3 symmetry. So on complete examples. So, but the aim of the work I'm doing with Giovanni Russo is to look at the case when we have T2 symmetry. So we have more examples to play with and potentially more room to find new cases. So good. So let me change slightly the perspective of the definition I had for the nearly Kähler manifold. So let me look at working with differential forms. So this gets us closer to being able to use something that's more symplectic-like and so on. So our convention is to call the 2 form associated to G and J sigma. So we put J in the first slot. And then the nearly Kähler condition, well, in any case, you can write that, take D of sigma and get a 3 form, which you will call psi plus. There's a convention to scale this by a factor of 3. And you can put J into every slot in psi plus and throw get another 3 form psi minus. So when you have a nearly Kähler manifold, then this combination of psi plus plus psi minus actually gives you a holomorphic. It gives you a 3-0 form, and it's a constant length. So this gives you a reduction of the structure group on the manifold to SU3. So the fact this is constant length is strongly tied to the fact that the metric ends up being positive Einstein. So one can rescale the G by a homothety so that you can normalize things so that the differential of psi minus is actually minus 2 times the square of sigma. So the natural remark here is that as soon as we have a symmetry of G and J, then it's going to preserve the constructions I've given here. So it's going to preserve the psi plus. It preserves sigma, and then it's going to preserve psi plus, and it's still preserving J, so it preserves psi minus as well. So all these differential forms and relations are preserved by any symmetries you have of the Hermitian structure. So in particular, there's a closed form around. We've taken psi plus as the differential of sigma. So this is the object we're going to think of as treat a bit like a symplectic form. And in particular, it's a closed three form, it's exact, and the primitive sigma, or a third of a sigma for psi plus, is also invariant under the symmetries. So one little remark is that if you know G2 geometry, this is no surprise, but it's easy to determine G from sigma and psi plus by a fairly direct formula. We have sigma as a Hermitian form, so the volume form is proportional to sigma cubed, and the inner product between two vector fields times sigma cubed is equal to this expression. So you contract x into psi plus, and contract y into psi plus. That gives you a couple of two forms that you can wedge together and wedge onto sigma, and that gives you the metric times the volume form up to the numerical factor. So this is a fairly is a nice compact formula. I don't know whether I don't have a particular reference for this other than that I've discussed it with some students. If someone knows a reference to this in the standard literature, that would be nice to have. But is a close relation or close cousin of the formula that gives you the G2 metric from a G2-3 form. Okay, so the picture now is going to be that we're going to take mostly work with sigma and psi plus, and that determines the rest of the geometry. So once we know the metric, then add sigma, we can get J, recover J as well.
Andrew, can I ask a question?
Of course, yes.
Is the expression of G symmetric in X and Y here?
Yes, it is.
Yeah, because, wait.
The contractions are two forms.
Yeah, right.
Which products are two forms is commutative. So, yeah. So that's exactly why it's symmetric. Yeah.
Yeah, I was just wondering if the sign was right. That's it.
Yep, the sign is fine. So, yeah.
Andrew?
Yes.
Claude here. It perhaps might be worth mentioning what the formula for the, if you look at the G2 cone, what the, the 3 form and the 4 form would be.
So I can try and scribble here somewhere. Yep.
Thanks.
So I'm not going to use the G2 cone actually, but if you think of this, the 3 form is phi. So so the cone you want the cone metric is a dt squared plus t squared times g. Yeah. And the 3 form here is, there may be a sign error in what I write here, but it's roughly dt wedge sigma plus psi plus. So up to your signs and conventions, but yeah. And the Hodge dual of that is a dt wedge psi minus. And then I think there's probably a half on the sigma squared. So
Andrew, I think you might want some powers of t floating around.
I may, yes, I do, don't I? Yes. So I want to make everything homogeneous. So I want t squared on the sigmas, don't I?
Yeah.
And I want t cubes on the psi pluses. Yeah. Otherwise, it's two product-like. So there's a t cubed here, and I guess a t to the 4th here.
Yeah.
Yeah. Good. Thank you. Yes. So as I said, I'm not going to use these, but it's nice to know the connection. So every time you have these nearly Kähler metrics, then you're constructing these Ricci flap metrics on the cone. So sorry about the mouse handwriting, but other questions or comments?
So in your setup, was there strong reasons why you didn't go for a T3 symmetry or a S1 symmetry, or is it just that happened?
Well, you'll see why with S1 in a minute. T3 has, we only have the one example, and it's there's nice results of nice structure results of Andre and Paul Andinaghi, but I don't have new things to contribute to that really. So the T2 is motivated by this list of 6 examples where we do have T2
By the way,
symmetry.
I think that that name is pronounced Nash rather than Nagy.
Okay, thank you. Sorry. Apologies to Paul Andy. But they have a nice paper with where they actually use something similar to what I'm talking about. So I'm going to write down a multi-moment map for the T2 action. When you have a T3 action, you have 3 separate T2s, if you like, generating that, and those combined give you 3 multi-moment maps. And they have a reasonably nice way to write down the nearly Kähler structure in terms of those multi-moment maps, and some local equations that are satisfied there. But there are various people that have tried to work on that and produce more solutions, and currently is open whether there are more solutions with T3 symmetry. From some other cases with symmetry rank, you might guess that maximal rank actually gives you a unique geometry, but that's not because I'm making a definite conjecture about the nearly Kähler case, but from cases like hyperkähler geometry and so on, if you have maximal torus of dimension n acting in a tri-Hamilton in a way, then sorry, that case is probably wrong, but there are other cases anyway where having maximal symmetry rank actually almost forces the geometry on you. So that's part of the reason we're looking at T2 rather than T3. But, okay. So I'm just interested for this talk. I'm just interested in torus actions. So I'm going to talk about multi-moment maps for abelian actions, and we're in the situation where we have a closed form of degree 3, and it has an invariant exact primitive. So in this case, we can actually write down the multi-moment maps in a simple way. So we can just think of we have in general, if we have an R form alpha preserved by some torus TK, then we can define a multi-moment map to be given this way. We map to a vector space. So this is the essential point in the definition of multi-moment maps, that we map to some vector space defined by the group. So here we take the dual of the Lie algebra, and here we have to we take the rth wedge product of that. So R here corresponds to the degree of the form alpha. Yeah. And we define this on simple wedge products, xy up to xr, from the Lie algebra to be alpha on the corresponding vector fields, x1 up to xr. So this is what I call a multi-moment map for the action. And this is a generalization of a moment map for in symplectic geometry when d alpha is a symplectic form omega. So, in that case, R would just be 1, and you're just evaluating the primitive on the vector field. So that's the situation where you have a symplectic action on a cotangent bundle, for example. Of course, generally you would want to take contractions of omega with vector fields from the torus and then ask for functions that differentiate to give that. But when I have the invariant primitive, then I get that free by just evaluating alpha on the vector field.
Should it perhaps be R+1 for the form?
So it's a multi-moment map really for a closed form of degree R+1. Yes. Yeah. So here's here's the general formula. If I take this map, then and differentiate it, then I get the differential of alpha evaluated on, which is an R+1 form evaluated on R vector fields. Yeah. So in general, you can define a multi-moment map for an R+1 form satisfying via this relation. So replace d alpha by the R+1 form. And then you have to postulate existence and so on. So when we have this set up, we also automatically get that this map is equivariant. So we're in the abelian situation, so it's just going to be invariant. So you can do this for non-abelian groups as well, but you have to cut down to a smaller subspace of lambda r here, corresponding to multivectors that vanish under the operation, the differential reduced by the Lie bracket. So, but this is the situation this is the setup I need for the this nearly Kähler situation. So when we have a T2 symmetry, then I'm going to call the generators U and V, and then the alpha I'm going to take is just going to be the two form sigma, which is invariant, and nu is just evaluation of sigma on U and V. So this just maps into the real numbers. So the notation is very slightly different here. I fixed a basis now, but I will still call this the multi-moment map. So now you see the reason for me not taking a T1 symmetry for this setup. I don't have naturally any closed one forms. I don't have any one forms naturally around to work with, which I could evaluate on a given vector field. So the smallest degree form I have is a two form. Good. So let's have a look at this map. So this actually satisfies a nice property on these nearly Kähler manifolds. This map is actually an eigenvalue for the Laplace operator. So it was actually Paul Andy that I think noticed this in the first place. And it happens to have a positive eigenvalue. There are various things in nearly Kähler geometry that fit well with the various Laplace operators. And this multi-moment map is a nice example of that. And more elementary property from the multi-moment map side is if we take this d nu, then the relation I said for d of these multi-moment maps tells us that this is uv contracted into d of sigma, but d of sigma was just 3 times pi plus, so it's giving d nu is given by this relationship. So you should think of psi plus as essentially defining you as some sort of cross product on the tangent spaces. Yeah. So the fact it's an eigenvalue for the Laplacian actually has a nice consequence. It tells you immediately in the compact situations, the average value is going to be 0. If we have compact manifold, then this is a continuous map, so the image has to be compact interval. But you actually get that 0 lies in the interior of this interval. Sorry. So this interval is strictly larger. So if it's not an interior point, then you get a contradiction out of that. So you nicely have that 0 as an interior point of the image of the multi-moment map. And what I want to take away from that at this point moment is if you use Sar's theorem, then it's going to tell you that nu has to have some regular values inside the interval AB. So I'm going to look at the geometry around regular points and then come back to what happens at critical values later in the talk. So let's take some regular value. Then let's set up a couple of connection one forms for the torus action. So I'm assuming this acts effectively, but S is a regular value. I should say it's a non-zero regular value. I forgot to write that on the slide. Set that. So let's just take this non-zero. So that automatically forces U and V to be linearly independent. And I can take some one forms that are dual to U and V and zero on their orthogonal complements. Think of those as connection one forms. So from this data, you can, and the nearly Kähler structure, you can construct three one forms. So we had 2 3 forms around. Psi plus contracted with U and V was just the differential of nu, but you can contract psi minus, so this is alpha 0, call this, and you can take contractions with U and V with sigma and take the components of those forms that are 0 on the span of U and V. So I will call those 2 one forms, alpha 1 and alpha 2. So they're actually given in this nice way. So these 3 forms, they're clearly invariant from the way I've defined them, and they turn out to be basic for the action. So they actually descend to the quotient, 3-manifold quotient, which is the level set quotiented by T2. So now we have a 3-manifold, and we get 3 linear independent one forms. You can recover the nearly Kähler metric from these forms and connection form data. So I'm going to call H for the metric on the span of U and V. So this is the matrix that I've collected thetas and alphas into theta 1, 2 and alpha 1, 2 into vectors. Yeah. So we have the metric here. We just have the metric on the orbits. Yeah. Here there's a horizontal component which is of the same type, but is scaled by a factor here. And then there's a ds squared term and an alpha 0 squared term with similar factors on there. So H squared is just our notation for the determinant of this matrix H, and H is just a matrix of inner products between U and V. So you can recover the nearly Kähler metric from these pieces of data, and you can write down the 2 form and the 3 forms as well. So you can recover the whole nearly Kähler structure from these items. So that gives you a hope that once you've reduced, you can actually reconstruct your nearly Kähler manifold completely. That's true. If we start with 3 linear independent one forms on a 3-manifold, then they have to satisfy some differential relations. So alpha 0 has to be a contact form. D alpha 0 is nearly alpha 1 with alpha 2, but there's a non-zero function that's allowed to multiply the pair. And that same function multiplied onto alpha 1 gives a one form with whose differential wedges with alpha 0 to give 0. So we get a contact, have alpha 0 as a contact form, and there are constraints on the differentials of alpha 1 in relation to it. And then you can choose any metric, which I should have called H. I changed my notation. Sorry. Should be H, what I called H on the previous slide. You can choose any metric H on the span of alpha 1 and alpha 2. Cover my mouse. And this data then determines a nearly Kähler structure with T2. What you have to do is take, you have to write down the metric that I gave on the previous slides, the forms there, but you need the coefficients. For example, this metric has to vary with the values of S, and how it varies is actually given by a geometric flow. So the flow corresponds to changing values of the level set of the multi-moment map you're at. So that's not so you're actually flowing by something that's not the unit normal. You're flowing by something that's proportional to the unit normal with a particular factor. So this is slightly different to the standard flows that are studied on these manifolds. So the actual expression for this flow is rather complicated, but let me write it down in a simple case, which is in the case when the three manifold is actually homogeneous with invariant data. So the relations up here actually force well, the polarization here actually forces Q to be a Lie group, and these relations up here would force Q to be a non-abelian unimodular group. So there's a nice short list of those, and the flow in this case is given quite simply for the alpha 0. It scales with a function here. This H is going to be related to the F up here. Sorry, there's a relation between the H squared is the determinant of this metric here, and S is related to F, comes from F and H. So alpha 0 just scales proportionally with time. The alpha 1 and alpha 2, that's what I've collected in alpha here, behave in a more complicated way, a priori anyway. So there's an identity matrix factor here, and then there's two matrices here. H is your symmetric matrix of the metric. P is a matrix that comes from the structure constants. And the metric is evolving in this way here. So it's quadratic in the H, and then there are factors in the determinant as well. So the structural constants here are given in this way. The alpha 1 and this F is now constant, so d alpha 1 and the d alpha 2 have a alpha 0 factor, and you can write these as P times minus alpha 2 alpha 1. So I didn't write it down here, but this F is related to the S by F being 4 H squared over S squared. H squared minus S squared. Yeah. So that determines your parameter S from these things. So I said a priori this was more complicated, this expression here, but it actually turns out there's an argument that you can actually diagonalize this in all cases. So you can change basis. So this the P and the H become diagonal, simultaneously diagonal. So we studied these equations a bit, but not completely, not fully. But let me show you an explicit solution in one case. So if I take Q to be SO3, I write the dual Lie algebra in this way. So I'm taking a basis E1, E2, E3, and D of E1 is E2 wedge E3. So then we can write down a particular solution. I introduce a new parameter, which is essentially a cosine of a double angle. And then the forms alpha 0 moves as sine of this this time. The sum of alpha 1 and alpha 2 and the difference of alpha 2 are the things that give the diagonalization, and they move with these factors here. So this gives us a cohomogeneity 1 solution on under the action of T2 cross SU2 on S3 cross S3. It is just the three symmetric metric on S3 cross S3 under this symmetry group. So that is an explicit solution, and you can sit and stare at this and think about what the boundary behavior is and so on. And, so we haven't fully analyzed this yet, but it's looking more and more likely we can analyze everything in this situation and describe what happens to solutions. So these are examples with T3 symmetry. It would not surprise me if these are the only solutions. So there is a classification of cohomogeneity 1, nearly Kähler manifolds in dimension 6, and which unfortunately has some holes in it. And this is also a hole in the classification. So this group is not one of the groups listed in the paper Podesta and Spiro, but it occurs directly on S3 cross S3. And there was some nice work of Madnick about cohomogeneity 2 actions on nearly Kähler 6 manifolds, where he has quite a good analysis of solutions of the setup in many situations. He has a cohomogeneity 1 metric hiding in there, which I'm fairly certain is this one. I haven't checked all details through, but unfortunately he dismisses it as due to it not being on the list in Podesta and Spiro. But, so any further questions or comments?
Sorry. So you're saying this one that you wrote down, though, you're saying cohomogeneity 1 with this particular action, but actually the isometry is large. The
isometry group is larger, yes. Yeah. So this solution has SU2 cross SU2 cross SU2 isometry group. Yeah. So, but it's constructed as a cohomogeneity 1 action. Yeah. Cohomogeneity 1 solution.
Podesta and Spiro didn't list this is simply because it has a larger isometry group.
I'm sorry, I wrote Spiro there. Yes, Spiro's right. If you look at their argument, they have a hole in their argument at this point, so they exclude it for other reasons. So it's not because they recognized it had larger symmetry group, at least what the way I've read there. So is a case they dismiss fairly quickly. Without going into details. So there were various other cases that are missing on their lists. I think we've been through and checked this now, and I think this is the last symmetry group that's missing. But also what I'm saying in this setup here is, yes, if you're in this situation, then you're always you can use our T2 reduction, and then the SU2 is commuting here, so that's going to descend to act on the quotient. So the quotient is always going to be SU2 or SO3. So it's going to come out of the equations. The solution is going to come out of the equations I had on the previous slide for this case. So, but there's still some work here to find decide finally whether there are other solutions or not. So I want to move towards thinking about critical values and so on instead of regular values, that's closely tied to what stabilizes the T2 action has on the manifold. So let's recall what we have. We have nearly Kähler manifold. We have T2 symmetry. I've defined the multi-moment map to be sigma on the two generators U and V, and we know the image is a compact interval containing 0 in its interior. So the stabilizers when the manifold is compact. Yeah. There are 3 classes of stabilizers, one in every dimension, 2, 1, 0. If the stabilizer is two-dimensional, then it has to be the whole torus itself. So you're getting fixed points. Or if it's one-dimensional, then stabilizer is actually connected, so it's automatically a circle subgroup. Or there is a possibility that you have finite cyclic subgroups. So the last possibility, you don't see that in any of the examples I've written down. I guess you could find examples, construct examples by taking finite quotients of some of them. But so the nice thing, the nice fact is that stabilizers of non-zero dimensions, so T2 and circle subgroup stabilizers, they only occur in this level set where the multi-moment map is 0. So the rest of the manifold is doesn't have stabilizers of non-trivial dimension, non-zero dimension, and the finite cyclic subgroup stabilizers they can actually they can't occur on the 0 level set. They can only occur outside. So so these T2s and circle subgroups, if you have a T2 that corresponds to a fixed point, and the local picture is the action of a maximal two-torus acting on C3 as a subgroup of SU2. So what you get there is you have a picture of a C3 where, let's try and draw C3. You have 3 complex coordinate axes. And if you look at the standard T2 action there, then you have a stabilizer that's T2 at the origin, and then on each of the axes here, you have stabilizers that are S1, different circles. So every T2 every fixed point actually comes with collections. So these are one complex dimension collections of points with stabilizer a circle, and these things, if you go to another T2 point, will give you a two-sphere inside. So these fit together in a nice way. So these fixed points, and the image of these 6 points and so on is a point and a line in the quotient, and they give you a trivalent graph. And the nice fact about this setup here is the T2 quotient of this is actually topologically smooth. So the T2 quotient is topologically R4. So we actually get that topologically this level set is a 3 manifold, and it gives this a smooth through 3 manifold, and it contains this trivalent graph corresponding to this these non-trivial stabilizers. So the points here correspond to stabilizer T2, the edges are stabilizer circles. Yeah. And you can nicely draw the pictures in the standard examples. So S6 has 2 fixed points. CP3 has 4. And the flag manifold has 6 fixed points. And then in the S3 cross S3 case, there are different choices for the two-torus you look at. There are cases where the two-torus acts freely, or there's just one circle of fixed points, or there are 2 circles of fixed points. So, and these pictures here also hold for the cohomogeneity 1 actions as well. And, so it'll be interesting to know whether other trivalent graphs could crop up at all. So I can't see my own heading here. Yeah. So if we're looking at critical points that are away from nu equals 0, then stabilizers are most finite there. And at any critical point, the two generators for the torus action become linearly dependent over the complex numbers, but not over the real numbers. So V lies in the span of U and JU. So, and this happens to be exactly the same condition for points to have a finite stabilizer, so finite non-trivial stabilizer. So if we have finite stabilizers, then the U and V satisfy this, and so we get critical points. The critical points away from the zero level set. So in the standard three symmetric cases, you can work out the complete picture here in detail. You can write down all the critical sets and all the information you have completely explicitly. So there are only two critical values outside of the zero value, and they occur exactly at the maximum and minimum of the multi-moment map. And both of these critical sets are pseudo-holomorphic tori, so generated by U and JU. And there is a nice symmetry here in that the maximal value of the multi-moment map is actually minus the minimum value. So this, you can draw this cartoon of these examples. So here you have some graph lying in the zero level set. The only other critical points are at the top and the bottom, and they're these pseudo-holomorphic tori that sit there. So it'd be very tempting to guess that this happens in all other examples as well. But unfortunately, the product two three spheres gives you plenty of counterexamples. So all sorts of strange behavior happens there. We have a rank 3 torus here. You can choose different two-dimensional subtori. And you can pull out examples where the minimum value here is not minus the maximum value. You can find examples where there are other saddle points. So there are examples where there are 4 critical values, none of them 0, but with some with saddle points in between. And there are also examples of 4-dimensional degenerate critical sets, so 4-dimensional critical sets. So we had hoped to be able to just directly apply a more theory picture to everything, but S3 cross S3 is giving us too many counterexamples to that. There's more work to do anyway. So the fact there are some degenerate critical sets and so on, you can control the degeneracy a little bit because you can compute some properties of the Hessian at critical points, and they satisfy this fairly nice relation here. That's essentially the 1-1 part of the Hessian is given by the metric on the orthogonal complement of U and V. But
Andrew, out of curiosity.
Yes. Yeah, please. Yeah.
So in the cases of CP3 and the flag manifold.
Yes. Yeah.
Tori, are they null homologous or they're?
Are they null homologous?
Because they don't intersect each other. It's sort of surprising.
They don't. No, that's right. Yeah.
With a Calabi-Yau non-integrable almost complex structure.
Good question. Good question. I hadn't thought about how they fit in. We know them completely explicitly, so I can you can look them up in Giovanni's paper. So they're written down and we know explicitly what they are. Off the top of my head, I don't remember, but it wouldn't be hard to look at that description there and decide to answer that question. But just off the top of my head, I don't remember.
Thanks.
I would guess they are not, but no. Let me retract that. I mean, homologous. I'd have to look in the computations. I don't think Giovanni or I have thought about what the statement is in that in terms of the homology. But it's a good question. That's a good question. Yeah.
No, we've never looked at that.
No. So it wouldn't take more than 5 minutes to sit down and decide that. Yeah. Okay, so actually this is my final slide apart from references anyway. So so we find this nice picture on the standard examples, but S3 cross S3 seems to give a counterexamples to any guess you might have about general behavior. But we have this little control over the non-degeneracy. So I'll stop here, and any other questions will be most welcome.
There are some questions. Andrew?
Yes.
You used psi minus already in this construction, but
yeah,
if you had a T3 symmetry, you can use psi minus to get a multi-moment map.
Right. Yeah. So that's exactly what Paul Andy and Andre do. So that's the function they call epsilon in their paper, and they use that piece of. They have a relation between that and the other multi-moment maps. So
you can reduce to a two-manifold then?
So you have 4 maps. You could reduce to a 2-manifold. They haven't done that.
Yeah, I'm doing that.
Yeah, you're doing that. Good. So what do you have?
It's an ongoing project, yes. And well, I haven't got that far yet, but I suspect it's an S2.
Yeah. Yeah, topologically, yes, I guess, yeah, I'd expect that, yeah, but yeah, so that's a very natural thing to do, yeah, Spiro, yeah.
Other questions from Montreal? Not at the moment, so perhaps some questions from the Zoom room. Okay, if not, let's thank Andrew again for this nice talk.
Thank you.